Okay, hello everyone. So this is most likely the last lecture on electric current and resistors. Uh, so the topic we're going to discuss today is EMF and terminal voltage. What is EMF? Electromotive force. The force that can move electrons or electricity. Electromotive force, EMF. This is an old-fashioned term for voltage. It means voltage. We don't, we know that voltage is not a force. It's more like a pressure, an electric pressure or an energy. But historically, back in the old days, researchers believed that there is a force that moving electrons or charge. So they came up with the word electromotive force, EMF. We still keep the word, we still keep the term, but now we know that it's not a force, but we still use it. Electromotive force or EMF is denoted by this Greek letter epsilon, or you know what this is, right? This letter. What is EMF actually? Let's see what the slide says. Electric circuit needs battery or generator to produce current. These are called sources of EMF. Battery is nearly constant voltage source, but does have a small internal resistance, which reduces the actual voltage from the ideal EMF. Now you probably noticed this. We talk about this during our lab activities, that it says 1.5 volts. You expect it to give two batteries together 3 volts, but when you measure it, it's lower than that, 2.9, 2.7, things like that. And when we are using the battery in the circuit, it even drops lower than that. So all these things can happen due to internal resistance of the battery. So let's go to the next slide, see whether there's any diagram. Okay. Alright, so the circuit symbol for a battery is this. Right? And then we say voltage is 1.5 volts or something. Now in a real battery, so if you take a voltmeter and measure it, we expect to see, if this is 1.5, if it is a good battery, we expect to see 1.5 volt reading. In an actual battery, so this is what it looks like, those batteries we used. So there's this symbol inside, so this is the battery, right? Positive side and negative side. But there is an internal resistance that we can't get rid of. There is a little resistance inside, internal resistance. We usually denote it by letter R, simple letter R. So when we measure this battery, when we measure it using a voltmeter, you are not directly measuring this. This is 1.5. Right? If there's a way to measure that, there's no battery inside the battery, it's the chemical reactions. I just use the symbol to indicate that. It does produce 1.5 volts, but some of that voltage is taken away by this little internal resistance inside. Again, there is no separate resistor inside. It's the friction or bad chemicals, whatever inside, takes away some of the voltage. So when we measure using a meter, what we are measuring here is terminal voltage. What voltage over here is the EMF. So EMF could be 1.5, right? But when we measure the terminal voltage, we might see 1.45 volts, something less than that, because this little internal resistor is taking 0.5 volts. 0.05 volts, sorry, in this case, 0.05 volts. is the little r. So that's the idea of internal resistance, right? So go back to the diagram, the PowerPoint. You see the battery, the resistor inside, the two terminals A to B. That's what we can measure externally using a meter. So if it is a good new battery, yes, we will see 1.5, but over time it builds up this little internal resistance, so that decreases the actual voltage we can get out from this battery. So we call it the terminal voltage, what really comes out. Okay, so that's the idea of EMF and terminal voltage. Okay, so pretty simple stuff. Let's try an example, see how this thing comes into math problems. Alright, read the example, give it a try. Battery with internal resistance. So let's draw the diagram. 65 ohms, that's an outside resistor. So this region is the battery. Here we have an internal resistance of 0.5 ohms, a small internal resistance, and the ideal voltage or the EMF going to be 12 volts. So this whole thing from here to here is the battery. This is the external circuit, the rest is the external circuit. So calculate the current in the circuit, the terminal voltage of the battery, the power dissipated in the resistor and the battery's internal and in the battery's internal resistance. So first let's calculate the current. If we didn't know about this internal resistance, if I say, okay, here's the circuit, here's the battery, 65 ohms and 12 volts, right? If we didn't know about the internal resistance, we would have calculated using V equals IR. So this is without internal resistance, right? Or disregarding the internal resistance. We're just going to neglect it. 12 equals I times 65. So current is 12 over 65, and 12 over 65, close to 1/5, close to 0.2, divided by 65, 0.184. Six amps, or you can say 185, 185 milliamps. In reality, let's come back to diagram 1. In reality, because now we know there is an internal resistance, it's given to us. So what is the current in this circuit? If you look at it, you see that this resistor is actually in series with this 65 ohm resistor, right? They're all in the same loop. So in this case, it's a series resistance. So what's the total resistance of the circuit? R total or R equivalent, it will be 65 plus 0.5, 65.5 ohms. This thing is in series. So what's the current? Voltage is still 12 divided by 65.5. So we have 12 divided by 65.5. We have 0.1829 amperes or 183 milliamps. A small difference, but yet noticeable because of this internal resistance. So it decreased the current in the circuit. Now it's asking part 2. Okay, part A is current in the circuit. The terminal voltage of the battery, AB. Call these 2 points A and B. What is the terminal voltage? Now without knowing all these internal resistances, we put the meter here and we expect to see 12 volts. If it is a good ideal battery, we expect to see 12 volts. But now what do we get? We put the meter like this. We really can't place the meter across these terminals, right? It's inside the battery. That's not going to work. So only way to measure it, the physically possible way, is to place the meter like this. So what do we see? There is a current of this many amperes in the circuit through the battery also. That's going to create a little voltage here. Let's find that. So that little internal, we can say internal voltage, right? That little voltage that this resistor creates, V equals IR 0.1829 times resistance 0.5. So this multiplied by 0.5 gives you 0.0914 volts. That's the voltage here across this resistor. So here we have a battery giving out 12 volts. There is a resistor taking away a little bit of voltage, 0.0914 is being taken away by this little resistance. So what do you get? Outside, the terminal voltage, it's a difference. So terminal, or you can say actual voltage, 12 minus 0.0914, 11.908 volts. In reality, because of this what do you say, internal resistance, it decreases the actual voltage of the battery, right? Okay, good. So this is what really happened during those lab activities. We saw that even though it says 1.5 volts, it doesn't give us 1.5 volts, so this is the reason. Alright, now let's see. You also observe that when we try to draw a lot of current, the battery voltage drops even further. Why is that? Let's say here we are taking this much current, right? Let's say we increase the current, we change the resistance in the circuit. Now we are taking current in the circuit. So it's a new circuit, right? This all change. Now the current, let's put a bigger number, let's say 0.4 amps, a larger current we are taking. What is the terminal voltage now? So here's the internal resistance, here's the battery, this is EMF, still 12, this is still 0.5 ohms. Current in the circuit is 0.4 amps. So the voltage here, voltage over here is current times 0.5. So what is it? 0.4 multiplied by 0.5. 0.2. So what's the terminal voltage? Terminal voltage 12 minus 0.2 gives us 11.8. Right? So the bigger the current we draw, the actual voltage drops. Imagine taking about 2 amperes. If we take 2 amps, internal voltage becomes 0.5 times 2, 1 volt. So the terminal voltage becomes 12 minus 1 becomes 11 volts. So the more current you draw, the voltage is going to drop. So that's why outside resistors we put some reasonable amount of resistance to keep the current at a desired level. Finally, it's asking the power dissipated in the resistor R, the outside resistor, and also the internal resistance. Okay, let's see. Let's mark the numbers we need. So we need this. We might need this. Let me erase the rest. Power dissipated in the resistor. So the outside resistor, this 65 ohms, has a current through it which is 0.183 amps, right? This current over here. So what's the power? P equals, we can use I squared R. Now here we can't do P equals VI because we don't know what the voltage across this resistor over here. It's not 12. Actually, we know what the voltage is. This voltage is 11.908. We can use this number over here. That's fine. It's supposed to be 12, but this guy is taking this amount. So the leftover, the big 11.9 is across the outside resistor. So we can do that. That's fine. Or you can do I squared R. You get the same answer. So 0.183 squared times 65, that gives you the power. Outside resistor 829, I get 2.17 watts. Power dissipated is actually energy release per second, right? Or the power emitted, power generated. Here this is a resistor, it's going to heat up, so it's dissipating energy. So that's why we use the word dissipated. For the small resistor, power is the same current, 183 squared, small resistance 0.5, 0.183 squared, multiplied by 0.5, small amount of power, okay. So most of the power still delivers to the big outside resistor, which is what we need. We want all the power to be delivered to the circuit. Little bit of power, little bit of energy is consumed inside the battery. The battery will also heat up in this process. If we draw more current from this circuit, if you look at this I squared R term, if there's more current in the circuit, internally it will consume more energy. So battery will heat up more, right? So to have an efficient battery means one with least internal resistance. So most of the voltage can be taken out as the terminal voltage. Okay, let's see what else we have. Alright, here's problems, resistors in series and parallel. We already discussed this. Now here we have a circuit. Actually these four diagrams, the same thing. It shows you how to solve this step by step. So if you read the question, a 9-volt battery, so here's the 9-volt battery over here, whose internal resistance is 0.5 is connected in the circuit shown. So the circuit has 5 outside resistors, 10 ohms, 6 ohms, 8 and 4, 5 ohms. How much current is drawn from the battery? So that's the question. How much current? What is the terminal voltage of the battery? What is the current in the 6 ohm resistor? Okay, this is a typical question. You guys have tried these kind of things before. give it a try. This diagram shows you how to reduce this, how to solve these outside resistors. You start here, 8 and 4. They are parallel, so we do 1 over 8 plus 1 over 4. We do the math and it comes down to 2.7. So here we have that. And then that 2.7 becomes series with the 6 ohm resistor. So we can add them together and make it 8.7. Third diagram over here. And that 8.7 and the 10 ohm above are parallel. So we again do 1 over 10 plus 1 over 8.7 comes down to 4.8. Now finally we have a like a full series circuit. Here's 5 here, 4.8. You can add those two together, make it 9.8, and then this internal resistor also become in series with all that. So add all together. So let's try this. Let's clear this. So finally it comes down to this. .8, 5.5. This can be written as 4.8 plus 5 is 9.8. So we have a single resistor of 9.8 and then little internal resistance of 0.5, the battery, which is 9, EMF is 9. Okay, how much current is drawn from the battery? You know what to do. Add these two together. 9.8 plus 5, 10.3 ohms. That's the total resistance in the circuit. So V equals IR, 9 volts. So once you add this internal resistance to this guy, it's taken out. Right now it's the whole, we have calculated the entire resistance of the circuit. So we can use 9 volts, the supply voltage, without a problem. Times 10.3, current is 9 over 10.3. 9 over 10.3, 0.87. So that's the current in the circuit. What is the terminal voltage of the battery? You know what to do. Multiply this current over here. Now go here. V equals IR. So 0.874 times 0.5. 0.437 volts. That's the internal voltage. So the terminal voltage, this always works against the battery, right? Battery is trying to push current this way. This resistance is, or voltage is against that. So you subtract. V terminal is 9. You can say EMF minus current times the little resistance. V terminal is EMF minus internal voltage. So we have 9 minus 0.437 equals 8.56 volts. Okay. What is the current in the 6 ohm resistor? Where is the 6 ohm resistor? Okay. Why don't you guys do that? And we can discuss this in class if you need to. Let me see if I have the answer for this. The 6 ohm resistor. Alright, let me see if I can find the answer to this without solving it once. Okay, it looks like the current through the 6 ohm resistor is 0.48 amps. I could be wrong. Give it a try, see whether you get this answer. Okay. Alright, so most of the math stuff is done. Let me see what else we have. Okay, so the final topic is more like a conceptual piece. We're going to talk about electrical safety. Something's very important. We talk about how to do calculations, circuit diagrams and all that, but if you don't know how to handle it safely, it's all useless. So, electric hazards. Here's some important stuff, especially EMT, first responders. They get a very thorough education in these areas. Most people can feel a current of 1 milliamp. Few milliamp of current begins to be painful. Current about 10 milliamp may cause uncontrollable muscle contractions, making rescue difficult. Around 100 milliamp passing through the torso can cause death by ventricular fibrillation. Your lab, one of the labs, is also talks about fibrillation, how to use the defibrillator. 100 milliamps can be lethal. Current above that might not cause fibrillation, but don't try it, because there is a certain ampere level that human heart responds. Above that, larger currents can pass through the body but will make severe burns. Household voltage can be lethal if you are wet. If you touch an appliance that is leaking electricity with wet hands and wet feet, you will be creating another path, a secondary path to the ground. So current goes through you, and that can be very dangerous. So in the lab, we do work with small currents in milliampere, 10 milliampere, even 100 milliampere level. Why it's not dangerous? Why can we safely handle it? Because we can even touch, don't try this again. We work with only up to 3 volt small batteries. That voltage is not enough to push anything through the human body. Resistance is big. So that's why we stick with the small voltages. No matter, again, this has been recorded, so I don't want to say much. It's safe, okay? But you shouldn't mishandle these batteries. There are ways you can increase the current and voltage and make them bad, but we don't do any of these. Household voltage, higher 120 voltage, it's big enough to push current through the human body. So that's why we have to be really, really careful. Now in US, it's 110 to 120. Certain countries, certain parts of the world, they use 230 volts, which could be even worse because it's a higher voltage, but they use lesser current. So there's pros and cons. It's a little cheaper to transport current at a high voltage, but these are country standards. Okay, so let's see what's next. A person receiving a shock has become part of a complete circuit. Now what's going on here? If you look at the second diagram, the lady by the sink is touching the hairdryer. Now hairdryer is connected to the wall outlet. So here's the wall outlet, here comes the power cord, and here's the hairdryer. Alright. Most of these things are made out of plastic. It's cheap, plus plastic is a good insulator. So the outer casing, even if there's an electrical leak inside, let's say the wire is broken and it's kind of touching the the surface from inside. Still, you hold it in your hand. You are touching the plastic outer casing, which is a good insulator, can protect you most of the time. The other thing, hair dryers are normally used around water in the bathroom. Even if it has all this protective stuff, if you touch it with wet hands, the water can leak through little openings in the plastic and complete the circuit. So let's say there's some voltage over here waiting to come out, and then these little water droplets can make the connection. So here's the person, not according to any kind of standard measurements, right? The other hand, she's touching the water faucet. This looks like a water faucet. Okay. The other hand is over here. So, and these metal pipes normally goes around throughout the house and are also going to the ground as well. So you are creating a conducting path from here through this all the way. You are creating a conducting path. So this sign is to say grounded. It's going to the ground. Electricity always wants to get to the ground. It's look for the least resistive path to do that. So if you create a path, current can easily go through you, and this is really bad. The take-home message: don't handle electrical stuff with wet hands. Don't keep them near water. That's why we don't allow liquids on the lab tables, because these tables have electricity. Even though all the safety precautions are taken, why take an extra chance, right? And if you have any doubts that there's some, it's broken or malfunctioning, get it tested before handling it. Okay, let's move on. Faulty wiring and improper grounding can be hazardous. Make sure electrical work is done by a professional. Okay, so what's going on here? The same thing I explained earlier, so let me clear this. So the hairdryer has a plastic casing, so that's good. That is some protection. Here, let's say this person is let's say this is some metal object, like it could be a refrigerator, it could be a washing machine or a dryer, tabletop microwave oven, something that has a metal casing. Metal is a conductor. So the wall outlet, here comes the power cord, here's the appliance, it's on a table, and here's the person. Like weirdly tall guy. So if the appliance is in good condition, electricity comes in, there's resistor or whatever, let's say some kind of electrical heater, goes through the heater, does its jobs, and returns back. So it's a continuous path. Okay, let's say, so this is good, and the person is touching it. Let's say there's some little broken piece of wire here, and it is in contact with the outer casing. So electricity is going in this path like it's supposed to. Also, it's on the casing, it's available on the casing, waiting to be grounded, right? So this return path is going to the ground over here. It's going back to the electrical company. But there's a parallel path is waiting to be connected. So you touch this, and the person touched this accidentally. Let's say he's barefoot, right? He's not wearing shoes. Shoes means some kind of insulating layer, like rubber shoes, rubber soles. Let's say he's not wearing. This leg is barefoot. So electricity has a shorter path, a quicker path, less resistive, so it's going to go through the person to the ground, and this is bad. So there's a good preventative mechanism in most of the electrical appliances, especially large appliances where a lot of metal outer casings. It's 3 pins. You might have seen this. We call it the 3-prong outlet or the 3-prong plug. It has a particular bigger third pin. It's called the ground pin. What's the purpose of the ground pin? Ground pin is actually connected to the outer casing of the appliance. So it goes like this. And internally it actually goes to the grounding terminal of the house. So every house or buildings has something called the ground path. All these ground wires, they come together and it goes outside your house, somewhere near the outer foundations, and there's a wire goes into the ground. So they put like a metal rod, couple of feet long, underground, and connect that wire into that. So if there's any electrical fault like this, instead of going through the body, it actually grounds through this. It will provide a much least resistive path. So it's really important to have this ground wire, right? It's a safety mechanism. And that's the other thing. When you work with appliances, it's very important. More than the supply wires, it's important that the ground wire is in good condition. Sometimes when you do yard work, accidentally you can, damage this thing. If this is broken, that's bad. That means it's not grounding. So if there's an electrical leak, it won't protect you. So be careful with these kind of things, right? Okay, so that's that. Let's see what else. Alright, so we don't need to get into that, all this detail, but this shows you all the colors. It's good if you know these things, but I would say a professional should handle these kind of repairs instead of we do it. With that is the end of this section. So thank you. Right.